for the lovely introduction. I'll just jump into it. I mean, Matt already mentioned a little bit about my background, but I just want to mention about myself a little bit too before we dive into flocculants. So I grew up in Istanbul, Turkey, this beautiful city that connects two continents, Europe and Asia, to each other through a sea. So I grew up by the water, and it makes me happy that my occupation is related to water as well. Then I got my civil engineering degree, the bachelor's degree from Istanbul Technical University, which is one of the oldest universities in Turkey. Then it was my dream to come to US for higher education. So my adventure took me to US to Iowa State. And that's where I got my master's degree. I joined Dr. Perez's group there. Iowa was too cold for me. As a research group, we moved down to Auburn. It was a warmer environment. I loved my time in Auburn. I got my PhD from Auburn University, where I did my research at this beautiful research facility, Auburn Stormwater Research Facility. Here are some photos from my grad school days, where I was flying drones, where I was building a flume, working in the lab, collecting soil samples. So I had a fun time during my PhD. It was a very hands-on experience. With that, my next location was Atlanta. So I joined GeoSyntec Consultants. I'm an engineer there working in the water resources group. As Matt mentioned, I worked with multidisciplinary teams to provide stormwater designs. I provide compliance support to our clients, both for construction and industrial purposes. I couldn't move away from Auburn, so I stayed close to it. With that, we can dive into flocculants. So due to the nature of disturbing activities and grading activities on construction sites, these sites tend to create a potential to discharge sediment into downstream water bodies. And according to EPA, construction sites tend to create an annual soil loss up to 100 tons per acre. With that, there are rules and regulations in place, and construction general permit requires us to implement stormwater pollution prevention plans on sites and incorporate construction stormwater management practices to minimize soil loss and capture sediment on site prior to off-site discharge. So where flocculants come into play, flocculants are one of the tools that we can use to help capture sediment on site by capturing fine-sized soil particles when we incorporate them with erosion and sediment control practices. These chemical treatment tools facilitate coagulation and flocculation. So let's talk about these mechanisms a little bit. So coagulation is a physical process that neutralizes the electronic charge on suspended particles. So soil particles tend to have a negative discharge. So when we introduce a coagulant into the system, they attract these particles through a physical process and neutralizes the electronic charge. However, flocculation is a chemical process. And when we introduce this chemical into the system, they build a bridging mechanism and they form larger flakes. We call them flocks, and they settle out of suspension through gravitational forces. I've just mentioned flocks, so we can see a photo of them from one of my experiments. So as I mentioned, when we introduce flocculants into a turbid sample like this, they promote flocculation and they create larger flakes. We call them flocks, and you can see them in here. And with time, they settle. So flocculants increase sedimentation rate and settling velocity, and thus they're decreasing the required detention time for these particles to settle out of suspension. But there are challenges while using flocculants. Here's a photo of me and the research team on one of ALDOT's sites looking at the condition of a PEM block. Flocculants are highly soil specific. That's one of the challenges. For example, in Alabama, there are 460 named soil series within 7 primary areas. On top of that, soils vary across a construction project as well. Since they're highly soil dependent, it becomes challenging to find the right product for the right soil type. And on top of that, a variety of products are available. So we look at flocculant types. There are synthetic flocculants. They're categorized based on their net charges. So there are cationic ones, positively charged, anionic ones, negatively charged, nanoionic, and amphoteric ones. And so a good example for a synthetic flocculant would be a polyacrylamide, which is commonly used for construction stormwater treatment. There are inorganic flocculants. They have low molecular weight. They have small size between particles. A good example for inorganic flocculants would be alum or bentonite type of flocculants. And there are bio-natural flocculants. They're based on animal and plant-based products. So a very good example to this would be a chitosan, for example. Commonly, chitosan is considered as a negatively charged like cationic flocculant. However, it's actually a bioflocculant, but it becomes activated by cationic charges. There are also stimuli-responsive flocculants. These are not very commonly used types in construction stormwater treatment, but basically these flocculants are being produced in lab environment by playing with their chemical characteristics. And there are also different forms of flocculants. There's a block form, there are sock forms, emulsion forms, and granular forms. So a lot of variety to choose from based on your needs on site. So to effectively use flocculants, we need to answer several questions prior to product selection and field application. So one of these questions is, what are mixing and agitation requirements? Another one would be, what are the reapplication and maintenance intervals? So depending on the product that you're using, these can change. So for example, for flock logs, flock logs need to be protected from the sun and sediment clogging, because with time, if they're clogged with sediment, they're not going to get dissolved easily. Same thing, if they're exposed to sun, they're going to dry really quickly, and they're not going to be able to, deliver the dosage effectively. And the other question is, are there environmental risks? Are we overdosing? Do we need to know the residual concentrations at the downstream end of the site? These are the questions that we should think about. There are also several application techniques out there. So here we're seeing some implementation from LDOT. So they use powders at ditch checks. They also use socks, downgrade of a ditch check as well. They utilize flocculants in sediment basins and slope drains. Another application of it is using them in storm drain inlet applications. So basically, they placed a pan block onto a pan, and they lowered it down to a drop inlet so that they can keep the log wet at all times. And then they can be used with sediment retention barriers as well. Here's another application. So they layer these straw layers with granular pan, so they can provide dosage. And also, it's important to know the passive dosing and the difference between passive dosing and active dosing methods. For construction sites, passive dosing methods are commonly used. Active dosing is providing more controlled and precise dosage delivery, and it's very commonly used for water treatment systems when they're using flocculants in that type of application. But on construction sites, passive dosing is more popular, which is a technique that is used to incorporate polymers into the sediment-laden stormwater. So basically, we're incorporating flocculants together with existing erosion and sediment control measures. So these applications would include erosion control practices with dry granular flocculants. It could be hydromulch with emulsified flocculants, They can be used as check dams with dry granular flocculants, and flog logs can be used in pipes, risers, or prior to a sediment basin. And flocculant dosing becomes creative sometimes. Here's another dosing method that we saw on one of the sites, is that they place these logs, and basically when flow comes through the system, it gets dosed and then agitated, and with that they provide appropriate mixing and agitation to treat the water on site. But another question is, do current techniques work? So we collected all of these questions, and that actually formed our research goal to develop guidance. So we decided to provide guidance specifically to ALDA for properly selecting flocculant type based on the soils on site. We also looked into providing guidance for delivery mechanism and mixing requirements. For this research, before we get things started in the lab, we wanted to understand the current status of the practice. So with that, we implemented a comprehensive literature review first, and then we also conducted a survey. So our literature review focused on flocculation mechanism, flocculant types and forms. We looked into current studies in construction stormwater management. We also read through state highway agencies' erosion and sediment control manuals, and we also looked into residual testing methods. With that, we formed our survey questions, and we distributed to the DOTs across the US. So out of 51 DOTs, we had a participant number of 37. So 39% of the DOTs indicated that they are using flocculants, they're allowing flocculants on their sites. And the main concern that we observed is that the ones that they were not using flocculants or hesitant to use flocculants were indicating that there's an unknown risk posed to receiving waters. So here's another result from the survey. We also asked about residual monitoring, and only 3 DOTs across the US is requiring residual monitoring. These are California, Florida, and South Dakota, and 10 of them do not require residual monitoring at all. We also asked about the guidance that they're using while deciding on dosage and product selection. So the majority is relying on manufacturer guidance. And then 2 of the DOTs have their own standard guidance for dosage and application rates. One of them is following toxicology limits that they have, and 3 DOTs do not use any guidance for dosage and application rates. These results help us to form our research goals and refine our research goals in a more comprehensive way, and we were able to prepare ourselves for the bench scale testing. So we want to do things right, and we want to start with soil sampling. As I mentioned before, flocculants are highly soil dependent, and because of that, we wanted to capture different soil samples across the state. So you're seeing 5 regions of ALDA, so north, west, central, east, central, southwest, and southeast. So we drove to all of these places to the sites that they have out there and collected soil samples. Required quite a bit of driving, but we were able to get all of the samples that we need on time. So the first thing that we did was prior to going on site, actually, we looked into this through USDA web soil survey. So we knew the locations of the sites, and we tried to understand the characteristics of soils out there that is available on web soil survey to see if it's okay, if it's going to match our analysis, and if we can predict soil characteristics without having to go to site in real life, like in a construction project. Prior to selecting a flocculant, can a designer, for example, go into Web Soil Survey and select a type? That was a question. But then we also conducted soil analysis to understand the physical characteristics of the soils. So we did a sieve analysis, Atterberg limits test, and a hydrometer test by following ASTM standards. And at the end, we also wanted to look into soil chemistry to understand the impact of cationic exchange capacity on flocculation. So we also conducted CEC analysis as well. So here's a comparison of Web Soil Survey versus laboratory tests. As expected, construction sites are very dynamic, so the soils tend to change across the site. So only for 2 of the soil samples, so we collected 12 soil samples from LDOT sites, and only 2 of them showed some sort of similarity to the physical characteristics. So this showed that we cannot just rely on solely Web Soil Survey. It's important to evaluate the physical soil characteristics through soil testing. As I mentioned before, we also looked into cationic exchange capacity. So we sent our samples to Auburn University's soil testing laboratory. They conducted this test and sent us the results. So cationic exchange capacity is a measure of cations that can be retained on soil particle surfaces. So the question in here was, can we use CEC, cationic exchange capacity, to determine flocculant selection? With that, so 3 of these soils showed high amounts of CEC per clay content values, and they were actually like cationic flocculants actually perform really well on these soils, for example. So it is important to understand the soil chemistry as well while evaluating flocculants. So now we're looking at the USDA texture triangle, and when we looked into the sample that we collected from LDOT sites, we realized that the majority was falling into the bottom left corner of this triangle. So we wanted to kind of have more samples to capture more variety of soils. So with that, we also added 3 more soils into our testing to capture more of this triangle. And then we went into bench scale experiments. So first, we conducted match tests. So to answer this question, actually, which products and flocculant types work with which soils? So for these tests, the purpose of it was to select top 3 best performing products for each soil. So we had 15 soil samples in total and 14 products. So we followed ASTM standards for the mixing procedures. So we flash mixed our samples in 120 RPM for a minute, and then we slow down our mixings for 20 minutes at approximately 60 RPM, and then we wait for them to settle for 15 minutes. With that, we observed color, flock formation, flock size, and settling velocity. And we created a point system based on these observations, and we ranked the products based on this point system, which I will show in the next slide. So as I mentioned, we looked into color, flock formation, size, flock, and settling rate. So for example, if at the end of the testing, if I was seeing that supernatant in the sample was light yellow, that would get 8 points. That means flocculant worked on it. And then flock formation, if it's forming quicker, it's getting a higher point. The size of the flocks are bigger, it's getting a higher point according to this point system. And settling rate is another category that we looked into. If it is the settling rate is higher, then it's getting a higher point. With that, we selected the top 3 products that we were able to test across all of the soils that we collected. So this is a summary of evaluated flocculant products. We had polyacrylamides mostly. As I mentioned, they're synthetic flocculants. We tested anionic polyacrylamides. Some of them were in granular form, and some of them we formed stock solutions to test them. And we also tested bentonite-based flocculant. We looked into chitosan. We also looked into combining chitosan with a coagulant agent. So those were in emulsion form. And then we looked into calcium sulfate, aluminum sulfate, and sodium montmorillonite. As you can see, dosage ranges are changing. So those are, before I explain dosage, I should mention this, that the orange circles that you're seeing are included in LDOT approved product list. So the dosage rates that you're saying, it varies. We reached out to the manufacturers and asked their dosage recommendation for the turbidity that we're going to try to treat in our testing setup and the amount of water sample that we're going to test in our testing setup. One of the manufacturers actually miscommunicated the dosage rate, but since we ranged the dosage for under dosage and over dosage conditions, we were able to capture the actual dosage rate for PAM. So that was resolved with no issues throughout the research. Okay, so with match test results, so this is a summary of what we were able to observe. So we selected, as I mentioned, top 3 best performing products, and the majority show that polyacrylamide across all of the soils was working really well. And in some of the soils, we saw that chitosan is also working well, and sodium montmorillonite as well. After completing match tests, so we selected our flocculant types that we're going to test in the dosage test. So the dosage test was trying to understand what is the optimal flocculant dosage we should be using. Again, we had the same test set up as you saw in the match test, but we used turbid water samples ranging from approximately with 1500 NTU plus minus 300 NTU. We use air-dried soils for this testing. We sieved our soils through a number 200 sieves so that we can just use the fines. And we used 1,000 milliliter tap water, and we set soil concentration based on initial turbidity readings. Here's an injection rack that we built for our testing. This was helping us to, if we are testing a stock solution, this was helping us to inject everything at the same time. With dosage trials, we identified, the purpose of it was to identify the optimum flocculant dosage rate, and dosage ranged between 0% to 200% of the manufacturer recommendation. Again, we had 15 soils with top 3 best performing products per soil, and we did 3 replicates of this testing, and we did again flash mix, slow mix, and settling phases per the ASTM standard. For this testing, we looked into turbidity, pH, color, and temperature. So now you're seeing a video of the flash mix phase. So we're 0% is the control. So the manufacturer, here's an example of it. Manufacturer recommendation is 5 milligrams per liter for this specific product. And then we ranged these throughout the testing. So we looked into underdosing condition and overdosing condition. Here's we're looking at the slow mixing phase. So at this point, you can see that flocks are forming, and 0%, 0 milligram per liter is our control jar. And once they settle, we collect the supernatant, and we looked into turbidity reduction of it, and pH, color, and flock size. So in here, here's another example with product E, which was a chitosan product. With a soil sample that we collected from LDOT sites. So the manufacturer guidance for this one was 50 milligrams per liter. And when we look into underdose condition with 10 milligrams per liter, we are actually reaching a substantial turbidity reduction. So it is important to know that in lab environment, we can see that, but maybe manufacturers are providing this dosage, considering that field conditions may create like product wash off, and field factors may impact this. So maybe they're providing slightly higher dosages, but it's important to know that we observed great performance in lower underdosage conditions. Here's another example. So in here we are testing another soil with 3 products A, E, and F. This is a PAM product, calcium sulfate and aluminum sulfate. We are seeing, again, with lower underdosage conditions, we are seeing sufficient turbidity reduction on this product. We looked into pH measurements as well, as I mentioned before. So in product A and E, we saw that, for E in overdosing conditions, when we are doubling the manufacturer recommended concentration, we are seeing that it's creating like some difference in pH, but it's not too substantial. Product A is also creating in one of the soils, it created a pH difference, but it was not substantial enough. But product N was significantly decreasing the pH of the samples. So with that, we really excluded this product from our further testing, and this product is also no longer in LDOT's approved product list. So it's important to look into pH while evaluating flocculants as well. So then the third thing that we looked into was residual testing. How can we measure concentrations being discharged? So first, we looked into using a spectrophotometer. So basically, I collected a control sample with known concentrations. I centrifuged them, and then I put them through a spectrophotometer and tried to relate flocculation with the results of the spectrophotometer. However, we realized that by the time I would rotate the samples and then place it in the sampling tube, and by the time spectrophotometer could send the beam through it, the flocks would form even with control samples, and they would settle. So we wouldn't be able to read the concentrations from them. With that, we changed our focus onto settling velocity. So we looked into Stokes law. Stokes law indicates that a particle travels in liquid under viscous drag and gravitational pull. So we said maybe we can relate non-concentrations to settling velocity. So we used a testing soil that we had available at our facility. We tested this soil, and the reason that we picked this specific soil because it was it had high clay content. It was a well-characterizable it had a well-characterizable color palette, and then it had a short settling period. With that, you're seeing our settling velocity observations. So I would create samples with known concentrations and then pour the samples through the graduated cylinders, and I would time it while they were settling. So with that, we were able to plot settling depth versus time. As you can see, the green data being displayed in here is showing a longer settling time compared to the flocculated samples. So with that, we calculated settling velocity based on this data, and we knew the concentration. So we created calibration plots to be able to estimate the concentration in an unknown sample. So with that, let's say we grab the sample from the field and we mix it with our testing soil. We observe the settling rate. So with that, we can calculate the settling velocity. And if the settling velocity, for example, is 175 inches per hour, we can put that to our calibration plot. And then that would estimate around 35 milligrams per liter of residual in this sample. So if the dosage rate was 50 milligrams per liter and the residual is 35 milligrams per liter, that would mean that residual application dosage was 70%. We did this for multiple products and got reasonable values to form our calibration curves. And I know that after I graduated, Auburn Stormwater researchers also did additional investigation on this, and they improved this calibration plus significantly. So let's talk about the findings of the bench scale testing. So we tried to answer which products and flocculant types work with which soils. Through soil assessment and bench scale testing, we were able to identify step by step what we need to do to select the right products for the soil types that we see. We understood that flocculants are highly soil dependent, and soil chemistry and soil characteristics play a role in this. And the second question we had was, what is the optimal flocculant dosage? Again, through bench scale testing, through dosage testing that we conducted, we observed the product variability. We looked into underdose and overdosing conditions, and we saw that in underdosing conditions, we can achieve substantial turbidity reduction. And we also understood the importance of evaluating pH while using and dosing flocculants. And the third question was, how can we measure concentrations being discharged? With that, we looked into settling velocity observations, and then we provided standardized residual concentration plots. So this really helps us to form a field applicable method to quickly test flocculant residuals on site. Then we took this into large scale evaluations. You're seeing a beautiful photo of our facility, which I took with a drone back in the day, but I'm sure a lot is going on out there and a lot is changing, so I'm excited to see it again sometime soon. So we took this into large scale evaluations, and we conducted flume experience to answer these research questions. The first question was, is proper mixing and agitation being achieved? Is a target concentration being introduced in the system? And what is the degradation of delivery mechanism? So here's the flume testing setup. So we first built the flume and calibrated, and then we had supercritical flow tests. Through supercritical flow tests, we tested four types of four flocculant forms: granular form, block, sock, and we formed an aqueous solution by using a granular product. And basically, we tested for clear water conditions, and we tested for sediment introduction. Then we recalibrated our flume and conducted subcritical flow testing. So again, we had clean water tests and sediment introduction tests through this setup. So here's a photo of the flume. It was a 40-foot long flume that we conducted at the facility. We lined it with plastic jute matting, and we also mimicked check dams into it to increase agitation and mixing. Here's the experiment setup. So as I mentioned, we had supercritical flow and subcritical flow testing. We use this testing to conduct our optimum dosage delivery experiments, and we also looked into longevity as well. For the soil, we had a control condition, which we used clean water, and then we had a testing soil at the facility that we utilized through flume testing. And for sampling, we had control samples upstream of the flume where we did not have any flocculant introduction. And we also collected samples from midsection, which represented low agitation condition, and then downstream of the flume, which represented high agitation condition. For measurements, we looked into turbidity and residuals. So these are the forms that we tested in supercritical flow experiments. So as I mentioned, we mimicked check dams throughout the flume, and we wrapped down with jute matting so that they can catch the flocks. So we had a sock that we formed based on the dosage recommendation. So we placed it right in front of the check dams, mimicked the check dams. And we had a solution. We used tubing and a pumping system to continuously pump solution into the system. And then we also zip tied blocks in front of the check dams as well, and we utilized powder on the check dams where they're receiving the concentrated flow. Here's a comparison of the clear water and sediment introduction tests. So we did clear water tests to just look into residuals, but for sediment introduction tests, we both looked into residuals and turbidity reduction. So here's a quick video of the supercritical flow experiments. So throughout the flume, we had 4 sampling locations upstream, ditch check 2, ditch check 4, and downstream location. So we collected 1,000 milliliter of undisturbed and disturbed samples. The undisturbed samples were tested immediately right after the test for turbidity, and the disturbed samples were taken into the lab, mixed in our mixer, and tested for turbidity and residuals. And now here's a video of the subcritical flow experiments. So for subcritical flow, we adjusted the slope of the flume, and we sampled from upstream of the ditch check. We had only 1 ditch check in here, and then downstream of the ditch check and downstream of the flume. Again, we had 1,000 milliliter of undisturbed and disturbed samples. And then we also looked into longevity, as I mentioned before, to answer what is the reapplication requirement for granular form. And we tested this in supercritical flow conditions, and the test duration was 2 hours. So with that, as I mentioned, with the disturbed samples, we took the samples to the lab and flash mixed down for 1 minute, and we waited for them to settle for 15 minutes and took the turbidity readings. And then for residual concentration monitoring, we separated the supernatant of the samples, flash mixed down with 1 minute with our testing soil, and then we observed the settling velocity and then related that to our calibration curves. Here are the snapshot of the results. So on this first chart, we're comparing undisturbed and disturbed samples, the turbidity reduction of them. So if you're seeing towards the downstream, if you're seeing similar values for undisturbed and disturbed samples, that indicates a good sign. That means that we were able to deliver the dosage throughout the flume. So for granular form, we were able to deliver it throughout the flume effectively. But then we also saw that with time, we are observing product washout. So when we looked into residuals towards the end of the testing, the granular concentrations were being lowered. So that indicated product washout. And we also compared clear water versus sediments. Of course, we are seeing more concentrations in clear water samples because flocks are not forming, but with sediment, flocks are forming and they're settling out of suspension, so then residual, the supernatant, has low concentrations. For block form, we observed that block is providing more continuous dosage throughout the flume, and again, we were able to deliver dosage at the downstream of the flume, comparing undisturbed and disturbed samples. For sock form, we did see that in undisturbed samples, we had less turbidity reduction compared to disturbed samples. The reason that we're seeing that, when I disturb them in the lab, the mixing machine is suspending it, and it creates more flocculation, and then they create better turbidity reduction. And then looking into the aqueous solution form evaluations towards the end, again, on this one, we have way more control over dosage because we're providing continuous dosage through this tubing system. And we were able to deliver the dosage effectively throughout the flume, and the residual concentration showed that we were able to control the dosage better compared to other forms. Then we compared the forms through statistical analysis. With that, we observed that there's a significant difference in turbidity reduction performance between flocculant forms. Block and granular tend to have more similar turbidity reduction performance, but aqueous solution is significantly different because it's more controlled. And then here's a result of the subcritical evaluations. Of course, since the condition changed, we were able to deliver the dosage throughout the flume easily compared to supercritical conditions. So the results indicated that, and also residual concentrations showed that in subcritical conditions, we can control the dosage easily compared to supercritical conditions. And looking into longevity testing, so this plot is showing each location that we sampled from upstream, discharge 2, discharge 4, and downstream locations. So with time, with granular product, the product is washing off. So we were able to calculate estimated longevity at approximately 4 hours, and then we calculated estimated treatment volume of this testing as approximately 1,400 cubic feet. With that, we were able to answer these questions. So is proper mixing and agitation being achieved? Upstream flocculant introduction is highly important. We should not be using flocculants downstream of the practices, especially prior to off-site discharge. We should allow distance between introduction and discharge location so that we are not releasing higher residual concentrations into downstream. And also this way we can promote agitation and mixing and floc formation. Is a target concentration being introduced? We validated that with through flume testing. We validated our bench scale testing results. It's important to have a complete flow contact with flocculants. And residual monitoring is essential if there's an agency that is concerned or if the regulation is requiring for residual testing, just to be sure that we are not overdosing. And what is the degradation of the delivery mechanism? Longevity tests come into play. We did a preliminary testing, but with more products, with more flocculant forms, I think longevity tests should be conducted in future research. And there's a huge difference in flocculant forms, so it's important to select the right product, but also right flocculant form for your specific application. With that, that wraps up the research that I conducted during my PhD, but if you have any questions, I'm happy to answer them.
Well, thank you, Billur. That was an excellent presentation, definitely eye-opening. So we are now opening up the Q&A session. So anybody who has any questions for Billur, you can open up that Q&A tab at the bottom. And Billur, are you able to see the Q&A on your screen?
I should be. Okay. Yes, I can. Okay.
So as the questions come in, if you don't mind just answering them, and then we'll get everyone's questions answered.
Okay, there is a question that asks, is the settled sediment considered a waste and thus be handled in accordance with applicable regulations? Or could the settled sediment be reused on site, for example, to regrade eroded areas? I did not, to be honest with you, I didn't look into this in my research specifically, but I know that on construction sites, there are some areas that these can be like reutilized. But it depends on like the regulations that you need to follow per state. So it could be utilized in my opinion, but there may be state-specific regulations that needs to be followed. Okay. Eric is asking, is soil type the largest factor for determining flocculant type? How does availability price come in? So what we saw in general is like there are certain flocculant types that are performing really well across the majority of the soil samples that we tested, for example, polyacrylamide. But while selecting, a flocculant, it's important to conduct soil testing to see if it's gonna perform well with your specific soil. Like within polyacrylamide products as well, soil testing comes into play. I do think that soil type is one of the largest factors for determining the flocculant type. How does the availability and price come in? I didn't look at the cost aspect of this throughout the research. I wouldn't be able to answer that off the top of my head, but I can look into it later and we can catch up on that, Eric, if you want to email me. But the availability meaning like there are lots of manufacturers out there, and like it's especially for construction stormwater treatment, flocculants have been becoming more and more popular day by day. So there are really well-known manufacturers out there that can provide products easily across the US.